All right, in this lesson, what we're going to do is look at the actual lengths of curves. And it sounds really complicated, but it's actually one of the easiest formulas that we can get out of calculus. And they can be tricky to work with too. So on all of these problems, the way that I'm going to solve them out, I'm going to go ahead and use a calculator to do the integrating for me. So just keep that in mind. And if your teacher requires you to work all these out by hand and show all the steps, go back and look at some of my other videos for help with some of these things. So here's what we've got. If we've got some sort of smooth curve that begins at A, the point AC, and ends at the point BD, where A is less than B and C is less than D, then we've got the arc length of that curve. And so if you just look at the curve we've got right here, sine x from 0 to 2 pi, we're talking about the length of this guy right here. And since he's curvy, we can't take a ruler to him and just measure. It gets really, really tricky to try and do that. But what we can do is apply a formula. And notice here we've got two variations. We've got one that's along x, like this one is, and we've got one that's along y. So if we want to integrate along the y-axis or have some sort of equation that says x equals, then we can handle that situation with the bottom equation. So we're prepared to go either way. And what's really nice about this is the only math really we've got to do is, it's part of our setup, it's pretty important, is we've got to find the derivative of this guy. So if y equals sine x, we need to know what dy dx is. And the derivative of the sine is cosine, okay? So we're going to take that and plug it into this top formula right here. We're going to plug it into the arc length, which is equal to the integral from, in this case, 0 to 2 pi. And we're going to go ahead and look at it as the square root of 1 plus y prime squared dx, or if you don't like y prime squared, you could have dy dx. Those represent the exact same thing. So here's our initial setup. We've got our y prime. Whoa, that's really ugly. Let me make it better. So we're going to go from 0 to 2 pi of the square root of 1 plus cosine x squared dx. And you'll want to make sure that your calculator is in radian mode, and as long as your calculator is in radian mode, you'll get the correct, and you punch it in correctly, you'll get the correct answer. So we're going to pause for 1 second. I'm going to punch this into your calculator, and we'll see what answer we get. Hopefully we'll match. All right, so if we're going to solve this guy out on our calculator, if you've got the TI-84, you're going to hit the alpha window button, and it's going to take you right to all these choices right here. One of those choices is Finance, choice 4, and we're going to go from 0 to 2 pi. And then we're just going to put in that big radical, so 1 plus, and then the cosine squared. And then lastly, fill in your variable. And if you've got an 83, you can do the same thing. You just go to the math menu. You put in where you start, where you stop, your function, and it should give you the same exact number. So there you go, integrating on the TI-84 for this problem that we're working on. Okay, so for this problem, I get 7.640 units of distance along the sine curve from 0 to 2 pi. All the problems in this section are going to work out just like this. They're really cool. So make sure you got your calculator handy, because it will take a lot of stress off of you trying to integrate the 1 plus cosine squared guy. All right, on this problem, we want to look for the exact length of the curve. So that's a little bit different than the first one that we were working on. With the first one, we were able to use our calculators and kind of do some cool stuff, but we're going to follow the same process. We've got a y equals equation, and since our equation says y equals, we get to use the y equals version of the length of the curve, and so I'll just write it out right here for us. The length of the curve is equal to the integral from a to b. In this case, it's going to be 0 to 1 of the square root of, and then it's going to be 1 plus y prime squared. Or you could also have dy dx in there. Okay, so remember, y prime is equal to f prime of x, which is equal to dy dx. So all of those can go into the parentheses there. This particular guy looks a little bit on the gross side. So what we're going to do is we're going to find derivative, which is, if you break it down, it's 4 square roots of 2 over 3 times the derivative of this part right here. So that's going to be 3 halves times x to the negative 1 half, sorry, to the positive 1 half. And then the derivative of 1 is 0. So clean this up a little bit, and you end up with the square root of 2 x to the 1 half power. Okay, that certainly doesn't look too painful. And so when we substitute it into our formula for the length of the curve, the exact length, then we're going to go from 0 to 1 of the square root, 1 plus, and then our derivative squared, so square root of 2 x to the 1 half squared dx. Here's the cool thing on this problem. When you square out this guy right here, the square root of 2 squared is 2. That's nice. And the square root of, whoops, there should be a 2 right here. So it's 2 square roots of 2. And the square root of x to the 1 half squared is just x. So we're actually going to work with a much simpler integral. The square root of 1 plus, and then 2 squared is 4, times the square root of 2 squared is 2. So 1 plus 8x dx. And the dx is not under the radical, so let me make that clear. Okay, so once we get this done, we can integrate that because now we're dealing with a situation where we've got 1 plus 8x to the 1 half power. And so when you integrate that, remember the derivative of 8x, okay, chain rule here. So we're going to reverse chain rule. Derivative of 8x is 8. So I want to put a 1/8 in front of this guy. From 0 to 1. And then this is just integrating now the square root of all of that. 1/8. So if I integrate a square root, I add 1 and divide by the new exponent. So this is going to be 1 plus 8x to the 3 halves divided by 3 halves. Okay? And how do I know that that's what it is? Because when I integrate 1 plus 8x, that's inside the square root. And so when I integrate a square root, I add 1 to the exponent. So 1 half plus 1 is 3 halves. And the 8 I account for with the 1/8 part. So then I divide by a fraction, which means I multiply by its reciprocal, which is 2/3. So I have 1/12 times 1 plus 8x to the 3 halves power, evaluated from 0 to 1. Okay, so I'm going to come up here where I got a little bit more space, and we're going to finish this guy off. Now I do my stop minus my start, so I stop at 1, so it's going to be 1/12 times 1 plus 8 times 1 to the 3 halves minus 1/12 times 1 plus 8 times 0, which is going to be 0 to the 3 halves. So it looks horrible, but it's really not too bad. So this is 1/12 times 9 to the 3 halves. Okay, that's the square root of 9 cubed. That's 27. Square root of 9 is 3. 3 cubed is 27. So 27/12 minus, and then 1. So 1/12. And that's going to give us 26/12. or 13 over 6. And that's the exact length of the curve, 13 over 6 units, whatever we're talking about, okay? That's it. It's not too bad. And if you punch it into your calculator to double check, you'll get whatever 13 divided by 6 would be as a decimal. Okay, what we're going to do on this problem is deal with a vertical tangent. And if you remember from the old school days, y equals 1/3 x, it looks something like this. We're going from -8, -2, which let's just say is here, to +8, +2, we'll say is here. This graph looks something like this. Okay, and we've got a vertical tangent right here at 0. We're going to have a vertical tangent when x equals 0. We can't handle that with a derivative because that's going to put a 0 in the denominator, and we don't know how to account for that. So what we can do to figure out the length of this line and still use the rules that we know about derivatives is we can solve this for x. Solve this equation for x. So to do that, we're going to raise both sides to the third power. So third power here, third power here, and now we've got y cubed equals x. What that does is it gives us a function that now we can use, and it makes a slight change so that we can not have that vertical tangent there. So it's basically, if I draw it on the x-axis, it's basically now saying, hey, we can look at this guy instead of a really flat guy here, okay? So use your rules. We know that the length of the curve is the integral from a to b, which in this case now is going to be the coordinates on the y-axis of the square root of 1 plus x prime squared dy. Okay, that's the only difference. So now what do we need? We need the derivative of x. So x prime is equal to 3y squared. Our derivative rules do not change, and we can make the substitution. So what does it look like when we get done? Well, we're going from -8, 2, -8, -2 to 8, 2. So those y coordinates don't change. So we're looking at an integral from -2 to 2 of the square root of 1 plus 3y squared dy. And I don't have a problem if you want to go ahead and punch this in on your calculator. If you want to simplify the radical a little bit, you can do that as well. So it's going to be -2 to 2 of the radical 1 plus 9y squared, or 9y to the 4th, dy. And when you punch this into your calculator, you can still punch in with x's. So that doesn't make a difference whether you do that or not, okay? And what I got on my calculator is, when I punch it in, I get that the length of my curve is 17.26 units. So there are instances when it's going to be easier to go ahead and change your equation from one to the other to do what you need to do. Sometimes it's easier also to stop at a specific point and start again. There's that option as well, as long as you cover all the bases, okay? So there you go, lengths of curves, not bad at all. Enjoy.